Welcome to The Explainer. You know, when we think about the massive industrial boiler systems keeping our modern world churning, powering factories, heating whole cities, we usually picture extreme heat, towering metal structures, roaring flames, the whole shebang. But here's the crazy part. Some of the absolute biggest threats to these multi-million-dollar behemoths aren't explosive pressures. They aren't raging fires. They are totally invisible. They're silent, and they literally attack the system from the inside out. Today, we're diving into a hidden piece of machinery engineered specifically to defeat these microscopic killers. We're talking about the Deaerator.
So to really understand this crucial machine, here's our roadmap for today. First, we'll cover the hidden boiler threats, then move right into defining the Deaerator and review its extreme operating conditions. After that, we'll break down the anatomy of the machine, trace the 6-step deaeration process, and finally wrap up with the big picture benefits.
All right, let's jump straight into Section 1, the hidden boiler threats.
Okay, let's look at the two silent killers lurking in everyday boiler feed water. First up is dissolved oxygen, or O2. Now, obviously we need it to breathe, but inside a high-pressure, high-temperature steel boiler, oxygen is a total nightmare. It causes severe, incredibly rapid pitting and corrosion. It literally just eats away at the thick steel of the boiler and the steam lines right from the inside. It's brutal. Then you have the second threat, carbon dioxide, or CO2. When CO2 dissolves in hot boiler water, it reacts to form carbonic acid. This acid fundamentally lowers the water's pH, which aggressively attacks the metal infrastructure and causes widespread thinning of the pipes. Bottom line, letting these two dissolved gases hitch a ride into your boiler means your multi-million-dollar system is going to effectively rust and dissolve itself into failure in a shockingly short amount of time.
Which brings us to Section 2, defining the Deaerator.
So what exactly is this machine doing? Well, a Deaerator is essentially a highly specialized, closed feed water feeder. Its entire purpose in life, its one big job, is to strip those dissolved gases, mainly the O2 and CO2 we just talked about, right out of the feed water before that water ever even touches the main boiler. And the way it pulls this off is beautifully simple in concept, even if it's complex in execution. It aggressively heats the water and forces it into intimate, really violent contact with steam. By jacking up the temperature of the water, the solubility of those dissolved gases drops off a cliff. Basically, the hotter the water gets, the less gas it can actually hold on to.
Now let's talk about the environment inside this thing in Section 3, extreme operating conditions.
The internal temperature of a Deaerator has to be maintained between 102 and 110 degrees Celsius. In engineering terms, this is known as the near saturation temperature. We are operating just barely above the normal boiling point of water at sea level. The whole goal here is to get that water as hot as physically possible without flashing all of it instantly into steam. This intense, relentless heat is the primary driver that forcefully kicks the oxygen and carbon dioxide right out of their dissolved state in the liquid.
But here's what's really fascinating. It's how the pressure works in perfect tandem with that intense heat. Inside the Deaerator, the pressure is maintained incredibly low, usually between 0.2 and 0.7 bar. I mean, that is just barely above normal atmospheric pressure. Why do that? Well, think about it. If the pressure in the tank was too high, the gases would just stay trapped inside the liquid, even at those high temperatures. So by keeping the pressure super low and the temperature near saturation, you create the absolute perfect physical conditions for those dissolved gases to break free and finally escape the water.
But you know, this physical reaction, it isn't instantaneous. And that brings us to a third, totally vital metric, residence time. The water typically hangs out inside the Deaerator for about 15 to 30 minutes. This isn't a quick sap. It's not a rapid filter. It is a sustained, relentless scrubbing process. The water literally has to sit in this highly heated, low-pressure environment long enough to make sure virtually every single molecule of dissolved oxygen and carbon dioxide is boiled out. It's a very precise waiting game. All right, let's open this thing up. Section 4, Anatomy of the Machine.
Let's systematically walk through the internal anatomy here to really build a vivid picture of how this works. First up, the spray nozzles. These take the incoming steam and blast it, ensuring intimate, really aggressive contact with the water. Next, you've got trays or packing material inside the tank. This is just brilliant engineering. It forces the water to cascade down and break apart into tiny droplets. That dramatically increases the surface area, meaning the steam can reach every single drop and scrub those gases out way more efficiently. Down at the bottom, we have the baffle plate. This makes sure the water mixes properly and doesn't just flow straight from the inlet to the outlet, preventing what engineers call a short circuit. Way up at the very top is the vent. This is absolutely critical because it safely releases all those separated, non-condensable gases out into the atmosphere. And finally, the inlet and outlet nozzles, which carefully regulate the massive flow of water and steam constantly entering and exiting the vessel. Every single piece plays a vital role.
So how does it all come together? Let's go to Section 5, the 6-step deaeration process. I want you to imagine just a single drop of cold feed water. Step 1, it enters the deaerator right through the inlet at the top. Step 2, instantly, steam blasts in from the lower headers and aggressively spreads upward through those spray nozzles we just talked about. Step 3 is where the absolute magic happens. That steam hits the cascading water, instantly jacking its heat up to that critical near saturation temperature of 102 to 111 degrees Celsius. Now, Step 4, because of this sudden, massive hit of heat and the low pressure environment, the water simply can't hold on to the O2 and CO2 anymore. The gases literally break out of the liquid, and since they're lighter, they naturally rise to the very top of the tank. Step 5, those destructive gases are safely vented out into the open atmosphere, totally harmlessly expelled from the system. And finally, Step 6, the purified, completely gas-free, deaerated water rains down, collects in the storage section of the tank, and is safely pumped out through the outlet to the main boiler. It is just a continuous, beautiful cycle of purification.
Let's zoom out now for Section 6, the big picture benefits.
This whole process brilliantly illustrates the ultimate payoff for industrial plants. By flawlessly executing this gas removal, the deaerator essentially accomplishes 3 massive things. First off, it drastically reduces boiler corrosion. We are talking about saving millions of dollars in pipe replacements and literally extending the life of the entire facility by decades. Second, because you no longer have all those tiny gas bubbles insulating the pipes from the inside, it significantly increases heat transfer efficiency. The boiler actually uses less fuel to heat the same amount of water. And third, it vastly improves overall plant reliability. When your internal components aren't constantly being eaten alive by acid and rust, you don't suffer from those unexpected catastrophic shutdowns. It's a total game changer.
It really makes you pause and think, doesn't it? We started off by looking at what seems like a pretty simple tank that just heats up water. But it turns out the deaerator is this active, continuous shield against invisible chemical destruction. Which brings us to a final thought for this explainer. How many other hidden machines are out there right now, operating in extreme conditions, quietly preventing catastrophic failures in the massive industrial plants that power our modern world? The invisible engineering all around us is absolutely staggering when you actually know where to look. Thanks for joining me on this deep dive, and as always, keep your curiosity sharp.